Experiment 9, pH determination of solutions, nature's indicators. There are lots of natural indicators in nature. Today we're going to look at using red cabbage juice as an indicator. You can do this with beet juice, you can do this with poinsettia flowers, you can do it with chrysanthemums. There's lots of things out there that have anthocyanins and other compounds in them that change color depending on how much acid is present. We're going to do this natural one, and we'll try a couple of synthetic ones, as well as standard old litmus paper and a pH meter, electronic version. So we're going to try this just by slicing up some of this red cabbage. We'll blenderize it and see what happens. I will time-lapse this so that you don't have to watch the entire adventure, but it's just a matter of cutting some and blenderizing it and filtering out the chunks and using the liquid. Put it in a little tray here and try and chop it up a little bit smaller before I throw it in the blender. Don't want to kill the stockroom blender. Knife safety here. You make sure you don't chop your fingers off. There we go. Alright. Got some pieces of red cabbage. So now we're just going to heat it, just because, generally speaking, things are more soluble at higher temperature. And so if we heat our liquid, we should get more of those pH color changing materials dissolved in our water before we filter out the chunks. Cabbage soup. Let's try straining what we've got and see if we've heated it long enough. So we'll just do a little rough test of our indicator and see if it's going to give us the action that we want by testing it in our first couple of compounds. We'll take our 0.1 molar hydrochloric acid, 0.1 moles of hydrochloric acid per every liter of water. So we know that that's going to be very, very acidic. And we will take our 0.1 molar sodium hydroxide, very, very, very basic. We'll just run a test and see what those look like, and we'll also get some data at the same time that we could potentially use later. All right, so I'll take the hydrochloric acid first. Wow. Okay. Cap up, as always, so that we don't contaminate. And we'll just put some of that into a test tube. aside with a pipette to use again later if we want it. We will take our sodium hydroxide with a different pipette. Whoa! Different test tube also would be helpful. And let's see if the magic works. We'll just add a couple of drops of our natural indicator to our hydrochloric acid. Look at that beautiful red color that develops. And let's try it with our sodium hydroxide. Same thing, a couple of drops. Look at that! Science! Natural indicator. Very basic, green. Very acidic, red. The picture in your lab manual shows very basic being yellow. Depending on where you look on the internet, cabbage juice turns beyond green to yellow in base, and as you go lower in pH a little bit, you get to blue. We'll find that out when we run some of our other experiments. But our indicator, at least rough test, acid base, seems to work very well. So now that we know that our cabbage juice indicator works, let's try it with the rest of our laboratory materials, and then we'll try it with a whole bunch of home materials and see what the pH of those are. We'll test it with the red cabbage indicator. We'll test it with Yamada's universal indicator. Got some of that. We'll test it with litmus paper, and we'll test it finally with a pH meter that will give us a digital readout of our pH. So we have our hydrochloric acid that turned our cabbage juice indicator red. We have our sodium hydroxide that turned our cabbage juice indicator green, although now it seems like it has definitely tended a little bit more towards yellow. So it took a little while for it to develop, but our cabbage juice indicator in strong base is yellow. It went beyond the green. Let's try acetic acid. I've got some 0.1 molar acetic acid. Let's put a couple squirts of that in the next test tube. I'll try and keep these test tubes lined up and organized so that I can check them with the other indicators, and we can compare and see how our indicator colors vary. If you look in the laboratory manual, you see that depending on your indicator, you can get very different colors. So that's the acetic acid. Next, and with our cabbage juice indicator, just a couple of drops, a 1, a 2, a 3, 4, just for good measure. I don't know if we're seeing any difference, really. Here's our hydrochloric acid, and here is our acetic acid. Acetic acid is a weak acid, so there's going to be less H plus present, even though this is also 0.1 moles per liter. This is 0.1 moles per liter HCl. HCl is a strong acid, meaning there's 0.1 moles of H plus in here per liter. This one is 0.1 moles per liter of acetic acid, but way less H plus. And you can see it is a lighter red, more pinkish. If we go to our next, which is deionized water, put roughly the same amount in there of deionized water, and add a few drops of our indicator. Look at that. Pretty much the color that it was in the jar, because I made our indicator in hot deionized water. So not surprising that we're purple in the middle. Ammonia, which is a weak base. So there are 0.1 moles per liter of ammonium hydroxides in here, or technically ammonias, and some of them are forming ammonium hydroxide. So there's not 0.1 moles of of hydroxide in here, unlike our sodium hydroxide, that there are 0.1 moles per liter of OH present. So we got our ammonium hydroxide. We will add a few drops of our indicator. Ooh, and look at that. It's a much greener blue color. Hold up some white paper behind it so you can see. This is a much green, you're seeing the shadow when I put it that close, right? A sort of greenish blue. So we've definitely, and if you watch the YouTube video that I've put in the folder as well, we've definitely got a nice little rainbow of colors here, going from strong acid red, weaker acid pink, neutral purple, weak base blue, strong base yellow. And we had green in the middle there before it had fully developed. Let's see if some of our household materials, where we can place them on the spectrum of colors, and also then what we can categorize them as. Acids, strong, weak, neutral, base, strong, weak, and I'll go from there. All right, so let's look at some various household materials, most of which are already on your data sheet, but some of them you might have to write in. We're going to check those with our cabbage juice indicator, and then we'll go back and check everything with our universal indicator and our litmus paper and then our pH meter. I'm going to leave them in the order that they are on the data sheet, even though that might not be in the order of the pH, because we got to try and keep these things straight. So, hand sanitizer, which all of us are very, very familiar with from these days. Grab it. So I got a jug of hand sanitizer here that says right on it 70% ethyl alcohol, and then the other stuff, inactive ingredients, are methyl ethyl hydroxyethyl cellulose, glycerin, hydrogen peroxide, and water. All that stuff's on the label here. So I'm just going to squirt some into this test tube. And add our indicator. It's a little thick, but we can shake it up and see what we get. Hand sanitizer. Very thick, so not mixing very readily, but we're getting there. Use a little stirring rod if we wanna. Thank you. But I think you can see that we're not really getting much of a color change. Right? Our hand sanitizer seems to be pretty darn purple. On to the next. Sugar water. Well, I've got some sugar, so I'll add it to a test tube. And add a little water. Okay, a little sugar in the test tube. A little deionized water. I put it in a test tube, or I put it in a little squirt bottle ahead of time. Give it a little flick to stir it. Add our indicator. Nothing. Not a whole heck of a lot of change. Just purple. We'll leave it, check on it later, come back to it. But sugar is not an acid or a base. It dissolves in water wonderfully, but no H plus or OH minus added to the water. So it stayed purple. Next up, vinegar. A 5% solution of acetic acid in water is vinegar, but let's go ahead and check and see if we see any difference between this and this that we checked before. That's going to have a lot of cleanup. A couple of drops of our indicator. Ooh. Now just to compare it. This one was the acetic acid from before. This was the hydrochloric acid from before. This is our vinegar. It seems that our vinegar is a little more concentrated than our acetic acid was. And so we were able to get, or honestly, actually, it may have been more dilute. With weak acids, it's hard to say which way you're going to go because of the Ostwald dilution law, more than we need to talk about in this class. But we've gotten, it's definitely an acid, right? Whether it's more red or more pink than the other hydrochloric acid and vinegar is, or acetic acid and hydrochloric acid, is a matter that we could debate in a more chemistry-intensive class. But definitely a nice red-pink color from our vinegar. All right, let's try a little lemon juice. Don't know if my wife's going to let me bring this back into the kitchen after having it in the lab. Probably shouldn't. Is it out of date anyway? Best by last month. So we might need to toss this anyway. Add a little lemon juice to our test tube. Oh, a little more than I had intended. I'm going to add some to a second test tube for later. Go ahead and do that now. All right, it's already yellow, so you're going to have to take that into account when I add the indicator. Let's see what happens. Lemons are citrus fruits. The citrus stands for citric acid, which is not on your data sheet, but we're going to try that as a comparison also. Definitely pink. As pink as this one? No. It seems more, this is more pink, this is more red. It seems like the vinegar is a redder, meaning more acidic in terms of this indicator, material. Just because it's in the news that lime juice is healthier for you than lemon juice, because people just make up whatever the heck they want in nutrition. For comparison, you're going to have to add this one in on your data sheet, if I can open it. Holy guacamole. Wow. My hands are notoriously weak, but I cannot open this. I'm breaking the bottle rather than getting the cap. Oh, I got it. I got it. Nearly had to call in the muscle. Let's try. Oh, those are extra lemon juice. Let's try lime juice. So write in lime juice on your data sheet somewhere. Try not to spill too much lime juice on the ground. Looks very similar to lemon juice when starting, right? You may have heard that limes are natural and lemons are genetically engineered. That's just not true. Crazy, people will say and put it out there. It's the wild, wild west in nutrition. Very few double-blind, placebo-controlled studies. limes or citrus fruits. So not surprisingly, get it to mix all the way to the bottom. There we go. Compared to lemon juice, to me the lime does look a little bit more acidic, but who knows? Both acids. That's lime juice we added in. Just for the sake of argument, I brought in straight up vitamin C crystals, 100% ascorbic acid, the active ingredient in citrus fruits, lemons, limes, etc. Let's see if that gives us any difference. A little ascorbic acid, solid. A little water so we can see it. Now, ascorbic acid is not particularly soluble in water, believe it or not. But we'll stir it so we get some in there at least. And we'll add our indicator. Oh, there we go. Thought it was going to stay purple there for a second. Definitely red. As red as the lime juice. Maybe even a little more so, but hard to say because this is a lot more transparent because there's no lime chunks or lemon chunks in it. So we're going to add in vitamin C onto your data sheet as well. Vitamin C, red. We did deionized water as part of our laboratory materials. Let's try tap water. Okay, got a sink right here out of frame. You'll have to trust me, I'm turning on the sink. Trying not to splash myself. And I got some tap water. Let's see how New York City tap water in a lab that hasn't been used in a couple of weeks behaves with our indicator. It's pretty well deionized because nothing in our tap water. It stayed nice and purple, which was the color of our deionized water. Tap water. Sodium bicarbonate, otherwise known as baking soda. Got it already mixed up in some water here. Let's check it. Ooh. Sodium bicarbonate. That's pretty darn blue, especially on the camera. In person, it's a very greenish blue. On the camera, it looks super, super blue. Interesting. Baking soda in water. It's a lovely shade of green blue or whatever you want to call this. On the camera it looks a little bit more blue. In person I can tell you it looks a little more green. Alright, your data sheet says Sprite. We already have seen the effect of sugar on water, that it didn't do anything, right? Here's our sugar water, just purple, no change to the indicator. So I didn't want to get a sugary drink, so I got just a seltzer drink that is completely colorless, but other than sugar and some other lemon lime natural flavors, this is identical, right? This has black cherry flavor in it. Let's see what soda does. So you can change your Sprite to black cherry seltzer water if you want, or soda water, or soda. We could try this with a Coke or something, but they're all going to be very, very, very similar. It's just the Coke would be harder to see because, you know, it's got the caramel color in it. All right, so our soda. Well, that's interesting. It didn't change much from the regular purple at first, but now, giving it some time, well, it's still pretty purple. Definitely not red. I was anticipating quite a bit of a redder color because soda is so corrosive. Interesting. It's pretty darn purple. That is way more neutral than I was expecting. We're going to leave this sit for a while and see if it starts getting more red. It's definitely on the redder side of purple. Okay, comparison. Purple. This was our water, and this is our soda. So we definitely have a red-er, pink-er, purple for our soda. Good one. Bleach is the next one on the list. I've got some Clorox. This is a scented bleach, and I looked at the label. It's got some other ingredients in it in addition to sodium hypochlorite. It's got some sodium hydroxide in it. So this is we'll see, but it's mostly bleach. It's definitely a household brand of bleach. Grabbed it out the linen closet, and here we go. See if I can pour it in here without pouring it on my black lab coat and making it get grossly spotted. There we go. And we'll check the indicator. A couple of drops. It's a little hard to see. And a couple more. That's not a color we've seen before. It's sort of a tan green, indicating base color, but I think that our bleach is so potent that it is bleaching our indicator, chemically reacting with it entirely and destroying the anthocyanins. But if we put it really close, you can see I'm going to add a little more indicator. See, right when it hits the top, it's an almost brown color. And then as I stir it in, it's definitely got that yellowish tinge to it that we saw with our sodium hydroxide at the top. Our laboratory sodium hydroxide and our bleach are similar. I just think that our bleach has got some other added ingredients in it that is making it a little tough to tell, but yeah, you can definitely see the yellow to it. I brought some Drano. I took it out of the regular bottle, but Drano is just very expensive rebranded potassium hydroxide. We tested sodium hydroxide. This is little pellets of potassium hydroxide. See down there? Yeah. Which is marketed under the brand name Drano. So let's test that and see why we need to keep our kids away from it. Add a little water to our Drano so that we can test it with our indicator. Stir our Drano a bit to dissolve it in the water. Happens a little slowly, but I think we'll still get a result right at the beginning here. Oh yeah, that didn't take any time. In the immediate green, we'll see if over time, as the Drano dissolves fully, whether this gets to be a little bit more yellow. But you can see this is the ammonia, the weak base. We're definitely more green with the sodium hydroxide than blue. Have we gone all the way to yellow of sodium hydroxide? Not quite. We definitely have a more green color for our Drano. You're adding Drano to your data sheet. If it's not already there, I might update the data sheet after I finish recording this. One more. I got some, at least they told me, 10 years old aspirin in water. Now, aspirin that's that old in water should smell like vinegar. And I can tell you from carefully sniffing the bottle that it smells like bottle. It does not smell like vinegar to me. So I have no idea. This is a true chemistry experiment. I have no idea what this is going to give us because it should have decomposed into vinegar by now. But maybe the aspirin is somehow still in the water in undecomposed form. I don't see any at the bottom of the bottle. But the active ingredient in aspirin is acetyl salicylic acid. So, if that acid is still present after 10 years, we should see a color change. Let's see. How about that? Totally worked. Aspirin in water. Okay. So we're going to run back through all of these materials, all of our household materials, as well as our laboratory materials with Yamada's Universal Indicator, which you have the colors of in your lab manual as well. And then we'll check it with litmus paper and check it with the pH meter. So I did not make you sit through me refilling these 5, 10, 15, 18, 17 test tubes again, but I've got everything all matched up so that we can compare the difference between our homemade indicator and our laboratory indicator. But first I want to test it with litmus paper. Litmus paper, very old school, it has a solution, kind of like of the beet juice, of a lichen known as litmus, that has been treated with acid or a base, dried onto it. So red litmus paper has been treated with acid so that it is, as you might guess from the name, red. If we dip this in acid, it's not going to do anything. It's just going to stay red. If we dip it in base, it's going to turn blue. Blue litmus paper, as you might guess from the name, has been treated with base. And it doesn't look super blue, but it's definitely not red. Okay? If you dip blue litmus paper in base, nothing happens. If you dip it in acid, it turns red. So we're going to try that in each of ours, all 17 of them. We're going to try it with red litmus and blue litmus. So you're going to have to fill in two things in the litmus column on your data sheet. If the red litmus changes, or if it stays the same, and if blue litmus changes, or if it stays the same. So here we go. In our 0.1 molar hydrochloric acid, what do you think is going to happen to the red litmus paper? Nothing. It stays red. Just going to use the other end. What do you think is going to happen with our red litmus paper in acetic acid? Again, nothing. What do you think is going to happen to our red litmus paper in deionized water. Nothing. What do you think is going to happen to red litmus paper in ammonia? Blue. What do you think is going to happen to red litmus paper in sodium hydroxide? Blue. Nice. Okay, keep going with the red. Red litmus paper in hand sanitizer. Nothing. Red litmus paper in sugar water. Nothing. Which means either, if nothing happens to red litmus paper, it's either acid or neutral. We don't know. It's inconclusive. We're going to have to check it with the blue. We've got our vinegar. Red litmus paper. Nothing. Lemon juice. Red litmus paper. Nothing. Lime juice. Red litmus paper. Nothing. Vitamin C crystals in red litmus paper. Nothing. Tap water with red litmus paper. Nothing. Baking soda, sodium bicarbonate in water, red litmus paper. What do you think's going to happen? Turn blue. Soda, red litmus paper. It says Sprite, but this is Schweppes. Black cherry, no change. Bleach. I have to get this on me. Big change. That turned very blue. Bleach, red litmus paper turned blue. How about Drano? Huge change. And last but not least, aspirin. Red litmus paper. Nothing. Let's switch over to the blue litmus paper. We should get the opposite results, right? Let's confirm. We've got our blue litmus paper in our hydrochloric acid. What do you think is going to happen? It's going to be hard for you guys to see. Yeah, I'm going to try and find a different thing of blue litmus paper because this is hard to see. Litmus paper gets old and hard to tell. Blue litmus paper with hydrochloric acid. What are you expecting? Maybe you can see that a little better now. All I can tell you is that in person, it has definitely turned pink. This blue litmus paper has turned pink. I don't know how well you can see it on the camera because the litmus paper is kind of old, but it is definitely blue where I'm holding it and pink where it's wet. You might have to just trust me. Blue litmus paper in, let's see if I have a different one that's a darker blue. A little better. Trying to find the bluest paper. All these papers are not that blue looking. So it's hard to tell if it's turning. Looking for the bluest blues. This might be it. All right. I'm going to go back. It says hydrochloric acid again, blue litmus paper. It turned red before, just confirming it with a different bottle. Oh yeah, this is much better. All right. So it's blue where I'm holding it. You guys can see that one on the camera. Hydrochloric acid definitely turned this blue litmus paper red. Let's try blue litmus paper in acetic acid. Very clear to see that the blue turned red with acetic acid. Blue litmus paper in deionized water. Nothing. No change. Blue litmus paper unchanged in deionized water. Let's try it in ammonia. What do you think is going to happen? Blue litmus paper, definitely blue in ammonia. So no change. How about in sodium hydroxide? Blue litmus paper. Definitely stayed blue. If anything, this shows you how not blue the paper was, where I'm hanging on to it. The blue paper kind of, with age, turned a little more red than it normally is. It definitely is blue, stays blue in sodium hydroxide. Let's try the hand sanitizer, blue litmus paper. What are we expecting? No change. So inconclusive. The litmus paper didn't change. The red litmus paper didn't change in the hand sanitizer, and the blue litmus paper didn't change in the hand sanitizer. That means either it's neutral or it's there's not enough water around to tell. Sugar water. No change. Inconclusive or neutral. Blue litmus paper in vinegar. We just did it in acetic acid. Should this be any different? Nope. It's definitely blue where I'm holding it, red in the vinegar. Blue litmus paper turned red in vinegar. Lemon juice. Blue litmus paper, what are you expecting? turned red. Blue litmus paper turned red. Lime juice. Blue litmus paper turned red. Vitamin C. Blue litmus paper turned red. Water, tap water. No change. No change. Baking soda. What are we expecting a blue litmus paper will do in baking soda? It stays blue. It's, again, where I'm holding on to it should be bluer to begin with. This is old litmus paper. The blue litmus paper stayed blue in baking soda, in water. Soda. See if we can tell anything. Blue litmus paper. Me, I can't really tell. I was expecting this to turn red, but I can't really tell anything with this. Hard to tell. Bleach, blue litmus paper. Still most definitely blue. Again, it should be bluer to start with, and it stays blue. That's our bleach. Drano. Blue. Still blue. And last but not least, aspirin. What are we expecting the aspirin to do? Here, our blue litmus paper goes definitely red. You can see it's blue where I'm hanging on to it. That's its original color. Should be even bluer, but it definitely turned red in the presence of our aspirin in water. So that's our two different litmuses. More qualitative. We can't get an exact pH. We can't get an exact pH with our beet juice either because, well, unless we have it calibrated, but you have the picture in your lab manual of the calibration of the beet juice, so you can get a approximate estimated pH from the beet juice. You can't do that with the litmus. It's either acid or base with the litmus, and that's it. But in concert with our beet juice, we can and our litmus, we can confirm whether it was acidic or basic or not. Next up, we'll check it with our universal indicator and our pH meter. Okay, so we have all of our materials, our laboratory materials and our household materials, and we've already checked them with our cabbage juice indicator. We've checked them with red litmus and blue litmus to confirm acidic or basic. And now we're going to check with a synthetic indicator, Yamadas universal indicator. We'll add a couple of drops just like we did with our beet juice. And Yamada's colors are different than beet juice colors are, as you can see in the lab manual. And we'll see what we get. Yamada is, at least today, the water that it's in is green, which I think is neutral, but we'll find out. We're going to add our Yamada's indicator to our hydrochloric acid. And we get very red color. Acetic acid. Also pretty darn red. Let's see, is it as red as the hydrochloric acid? You know, pretty darn the same to me. A little bit different red than our beet juice. Okay, here's our beet indicator with our acetic acid, definitely more pink. Yamadas Indicator with acetic acid. Yamadas Indicator with water, deionized water. So the green color is our neutral color with Yamada, and our neutral color with beet juice was purple. Different colors. Indicators indicate differently because they contain different compounds. Our beet juice was more purple when it's neutral. Our Yamada's indicator is more of a yellowish, greenish, whatever you want to call that. Hold up the white paper back here. Yellowish, greenish. With weak base, ammonia. There's where we see a purple color for Yamada. And our strong base, very, very deep purple. Okay, so that's sort of a way of, with laboratory materials, to calibrate our indicator so that we can determine what the pH is of our home-based materials. But you know that oven cleaner is incredibly basic, and that citrus fruits are incredibly acidic, or most, very acidic. Not as acidic as hydrochloric acid. So those could be your starting points for checking things at home. We'll look at our household materials, though, with the laboratory indicator. There it is with hand sanitizer. Just kind of, well, depending on how we shake it. Let's see. Might need to stir this. It's very strange brownish, reddish color, depending on where it is in the hand sanitizer. It's green down there, but red up here. Let's see if I can. It's got hand sanitizer on it, yeah. Stir it up, it's just so thick. It's hard to tell. Sort of an orangey yellow. That's interesting. With Yamada, it's a different color. That was it with beet juice. Hand sanitizer, sugar water with Yamada. That same sort of, this is the hand sanitizer, more of a yellow. This is more of a reddish color. Is it as red as our acetic acid? It might be. Weird. That's a strange result for sugar water. We didn't expect our sugar water to be acidic. Our sugar water before definitely has not been. Maybe our test tube is contaminated, or maybe we're just getting anomalous results. We'll have to keep going and see. Vinegar. Definitely red. Is our vinegar any different than our acetic acid? Let's see. In person, this one looks slightly more red. Our vinegar looks slightly more red than our acetic acid. When we did it with our beet juice, we had the same situation, right? This was more red with the vinegar than it was with the acetic acid. Lemon juice. Let's see if we can finally see a difference between lemon and lime. Definitely a red, reddish orange. Lime juice. Not quite the same, but still pretty reddish orange. Get it mixed down in the bottom. When we did it with our beet juice, lemon juice, lime juice, slightly different reds. Lemon juice, Yamada. Lime juice, Yamada. Those are almost identical. Vitamin C crystals. the active ingredient. There you go. Regular old tap water. Unchanged, not surprisingly. Baking soda. Ooh, that is a very dark purple. We couldn't tell with the litmus. The second one, the blue litmus, the red litmus changed to blue. The blue litmus, we couldn't really tell what was going on. Definitely can tell here. Baking soda. Sprite. Sprite with Yamadas Indicator. There we go. Now that's kind of what we were expecting. There's definitely some pink, red going on there. Bleach. Incredibly blue. Very, very, very blue. The Sprite, the baking soda, definitely more purple than blue. Baking soda is purple. The bleach is more of this blue-green. Drano. Whoa, that's an intensely dark purple. And finally, Aspirin. Haha, not surprising that acetyl salicylic acid, or acetyl salicylic acid, depending on how you pronounce it, even though it's 10 years old, nice and red. Our final check will be with a pH meter that you can absolutely estimate based on the colors of the bead indicator posted in the lab manual, based on the colors and pH values of the Yamadas indicator posted in the lab manual. You can do an estimated pH and the change to the litmus. And we'll check the pH meter reading and we'll see if those match or if our meter needs to be recalibrated or what. Our final check is with our pal the Vernier, which this time has a pH probe hooked up to it. Now the pH probe is very delicate. It's based on conductivity, how it measures, and so it's stored in a buffer that should be pH 4 or 7 or 10. And this one is probably the pH 4 buffer, which it holds its pH at roughly 4, and we have a reading of roughly 4, so I think we're going to call it good enough. I'm going to rinse my pH probe. There's a little glass piece in the bottom here that you want to always keep wet. You don't want to break it. That's why it's got this plastic guard around it. And you want to rinse it off in between each reading because you want to make sure that your reading is what you're actually measuring. So I'm rinsing it off, and you can see that the pH is definitely changing. When you expose it to air, it reads differently, and also I'm rinsing it with deionized water, so it should be reading around 7, and in fact it is. So will our reading be exactly reliable? We haven't calibrated our meter. Like I said, it should have been reading 4. It was reading a little bit under that. It should be reading 7 now. It's reading a little bit under that. So it seems like our meter might be reading a little bit low, but we can definitely rely on it somewhat qualitatively. If it's below 7, it's probably acidic. If it's way below 7, it's probably very acidic, and so on and so forth. So we'll check with hydrochloric acid, which should give us a reading of around pH 1. Hopefully the meter will fit. Stir it around, make sure there's no air bubbles underneath it. And we've got a reading of, oops, all right, cancel, under 1. Which again, it seems like our meter's reading a little bit low, but that's great. So your pH meter reading is 0.70 in 0.1 molar hydrochloric acid, which is not entirely off from what we would expect, which if you do the math, which we don't do in this class, is a reading of 1. So I'm just rinsing off my probe. How far it went back up? Not very, right? It's still a pH of 2. We don't need to get it to 7 in between, but I might want to get a little more deionized water and give it just a dunk in that, rinse it off. Still pretty low pH, but that's all right. Like to get a pH closer to 7 in deionized water before I go back into my next compound. But deionized water doesn't take much contamination for it to start reading crazy, so I think we might move on. Yeah, 4.5. All right. So into our acetic acid. Get air bubbles underneath. And pH of 2.3. Let's call it 2.3. You guys reading that? Yeah. 2.3. Somewhere in there. For acetic acid. Not surprisingly, given that it is a weaker acid than hydrochloric acid, we're seeing a higher pH. Let's check deionized water. Now again, deionized water with slight contamination can give us some wacky readings with our pH probe. So we'll see what we get. Our indicator color with Yamada was a nice yellow-green, as you can see. With our beet juice, it was a nice purple, unchanged from the deionized water color. So hopefully we'll get a pH reading of 7, but if we don't, it's an instrumental issue. It's not anything for us to be really concerned about. But that's unfortunately the hazard of working with electronics sometimes, is that without proper calibration, you can get misleading values. Now this looks like our deionized water is around pH of 4. I really don't think that it is. What should we record? I mean, we can't just make stuff up. So on our data sheet, I think we have to record. Well, it's still increasing. Let's wait. Let's wait a little while. I'll vamp, or I'll pause the recording, and we'll come back to it in a minute or two. All right, we've waited a minute or two, and our pH is still in the mid 4s. I'll call this 4.4, and still rising. But I don't know if you can see, our indicator has changed from yellow to red. The contamination on my pH probe, even though I rinsed it, there was enough contamination. Again, it doesn't take much contamination to really mess up deionized water. The contamination on the pH probe, I think that our deionized water was 7 when it was yellow, but now is around a pH of 4. So what should you record on your data sheet? You record what you observe. That, it's pH of 4.4, asterisk, but the indicator color also changed to red. So our probe contaminated our sample. Give it a little rinse. I'm going to get some more deionized water and rinse off the probe. And go into ammonia. What are we expecting? check it. $10.9. It's still rising a little bit. Oh, I'd call that 10.9. 10.9 in ammonia. I'm going into an even stronger base, so I'm not going to bother rinsing this one. Into the sodium hydroxide. And make sure we got no air bubbles. 13.7. 13.7 in NaOH. All right. That's it for our lab materials. Rinse. Try and get our probe back more towards neutral before we go through our household materials. Takes a while for a pH probe to equilibrate, so I'll pause the recording and we'll come back to it once it's equilibrated a bit more. So even after about 5 minutes, our pH probe still is reading pretty basic from our last reading. So we just gotta be a little bit cautious about jumping in between acids and bases. So I think I'm gonna start with our bases, since we're already basic, and work more towards our acids and see if we can get readings that are at least somewhat reasonable. So I'm gonna grab, this is Drano. Drano, so we're not going in order. You have to be careful as you add your numbers. So Drano. And our reading is 13.6 at least. Yeah, 13.6 for Drano. Hopefully I won't skip any. Cleaning off the probe, giving it a rinse. Here's bleach. Again, I think it oxidized our thing just because it's so harsh. Let's see what our reading is. 12.9. 12.9. Bleach is sodium hypochlorite, not sodium hydroxide. Although this bleach actually has a little sodium hydroxide in it, along with some detergents and stuff. So it's not surprising that it's not quite as basic as the Drano was. Let's try the baking soda. Baking soda. Again, sodium bicarbonate is not quite as strong of a base. 10.0. 10.0. Baking soda. I think it's going to go any lower, is it? Yeah, pretty steady. 9.9, 10.0, somewhere in there. Baking soda. Let's look at our more neutral ones now. Try water. Alright, see what that gives us. May not be enough equilibration time, and again, contaminating this with our probe is a distinct possibility. We're still green colored. We're dropping, but I don't think we're going to hit 7, which we would expect. Oh, it's dropping. Oops. 8. 6. We'll give this a minute. We definitely have the green color of our Yamadas indicator, which indicates more neutral, and we're steadily dropping. At some point we'll just have to call it, though. For that, as low as we could get it with our meter, given our contamination. We might get there. Still dropping through 8. Yeah, we're into the 7s. Alright, I'd be willing to call this neutral. I know we haven't quite hit 7.0 yet. We'll give it another minute. I think we might get there. We might get under 7. Let's see. Yep, down in the 6s. Well, I'm satisfied with calling this a 7.0 for our tap water. Not going to rinse it because you can't get any more neutral than that. What other ones did we have that were semi-neutral-ish? Well, we contaminated our sugar water with our... oh wait, no, that was our other thing that we contaminated. Let's just... yeah, we'll do all the other acid ones, I guess. Let's start at this end. Here's our aspirin. Our aspirin in water is looking like it's around... wow. Pretty low. Will we get below 2? Nah. We'll call that a 2.0. Hopefully not your GPA. 2.0 for aspirin in water. We did bleach. We did Drano. We did bleach, I hope. Now I don't remember. Did I skip bleach? No, we didn't skip the bleach. Sprite. Just going straight in without a rinse because we know we're somewhat acidic. Oops, spilled. I think we can call that a 3.0. 3.1. 3.1 for Sprite. Baking soda, water, vitamin C crystals. Vitamin C crystals. Looks like we could call that a 2.0. Oh, we dropped a little under. Nah, I think we can call that a 2.0. Vitamin C crystals. See if that's any different. Again, I'm not going to rinse just because we're in acids and it'll work. Minor contamination. This is our lime. Slightly higher at 2.2. I don't know. I don't know if I trusted the hundredths place on this thing. I think I'd call that a 2.0 also. Lime juice. Vitamin C crystals, identical, 2.0. Lemon juice. Maybe slightly higher at 2.1. Maybe. Vinegar. Well, that's surprising. I thought that'd be a little higher. It's like about a 1.9. Yeah, 1.9 for vinegar. I am going to rinse now because we're going into stuff that's more neutral. Should have done these in the middle. Sugar water. Might not spill. Definitely higher. I don't know if I trust this one with contamination of the probe. We were in pretty acidic before. I would think that this would be neutral. I think this is an anomalous reading. Doesn't seem like it's climbing anymore. I think we're going to have to call it a 3.6. But I don't know if I trust that value. 3.5. It's holding pretty steady. 3.5, but we might have contaminated our sugar water with our probe. And last but not least, our gooey hand sanitizer. See if we can even get a reading. Oh yeah, dropped some. Oh, no. At a 3.5 also for the hand sanitizer. Maybe 3.4 for the hand sanitizer. Again, I would expect that to be neutral. I think we've got a little contamination of our probe going on at this point. But that should give us enough information with a variety of techniques to get a pretty good idea of the pH of these things. 3.7 now. Yeah, I think our hand sanitizer should be a bit more neutral than that based on our other more qualitative tests. Our Yamadas Indicator, our red cabbage indicator, and our litmus tests showed that it was pretty neutral. We've gone a little bit orange here with our Yamadas Indicator. So I think contamination from the probe is why we're now seeing, I'd even call this 3.9 at this point. The longer we wait, I think the more neutral it's going to get. But I don't feel like waiting anymore. Patience is a definite virtue in the lab, but I think we've done this for long enough. So I leave it to you with that.